Calculus class. Today we're going to learn topic 45, volumes of solids of revolution with what's called the washer method. So, volume by washers. So, a washer basically is a disc with a hole in it. So, it's pretty similar to the disc method, except that we are going to have to deal with an outer radius and an inner radius, because we want to find the area of the face of this washer. So you'll see that we have a big circle and a little circle inside of it. So typically, if you wanted to find the area of the shaded part without the hole, you would find the area of the big circle and find the area of the small circle and then subtract the small circle away from the big circle. So this part right here is our change of x, just like before. The thickness of the washer or the cylinder is your d of x, because you're going to have infinitely many of them. All right, so we have what is called an inner and an outer radius. So starting from the origin and to the smallest circle, that's going to be my inner radius. So we're going to call that little r. And then from the origin to the outside of the large circle, that's your outer radius, and we're going to call that big R. And to keep in mind, you want to find the area of the 2D cross-section, like I said, the face, and you would find the area by taking the area of the outer circle minus the area of the inner circle. And if the cross-section is a washer, we find the inner radius and the outer radius of the washer in terms of x or y. And we use the area of the bigger circle, right? So pi r squared, where r is your outer radius, minus pi r squared, where this time your r is your inner radius. So to give a more formal definition, if the solid consists of adjacent vertical washers between x equals a and x equals b, we find the outside radius, big R of x, and the inside radius, little r of x, of the washer at x, and the volume is classified as pi times the integral from a to b of the outer radius squared minus the inner radius squared. So this right here is representing the area of the big circle minus the area of the little circle. So visually, what this would look like, I have two functions, and I'm going to rotate this area bounded by these two functions around the x-axis, then that means my outer radius is the radius that's furthest away from my axis of revolution. So in this case, the top curve. So just keep in mind, the outer radius is, you want to use the curve furthest from the axis of revolution and the axis of revolution. So that means you're going to take top minus bottom. So in this case, your big R is your top curve minus your axis of revolution. And then your inner radius is going to be the closest curve to the axis of revolution. So to get the inner radius, you're going to take bottom curve minus the axis of revolution. And of course, you can also have horizontal washers between y equals c and x equals d, and we find the outside radius, r of y, and the inside radius, little r of y, of the disk at y. So this time it's basically the exact same thing, but in terms of y. And visually, that means you're going to have horizontal washers or rectangles. This time your inner radius it's still the curve that's closest to the axis of revolution and your axis of revolution. So this would be the blue curve minus the axis of revolution. And your outer radius is still the curve that's furthest away from the axis of revolution minus your axis of revolution. So rotation around an axis. So for all of these examples, we're going to use the same two functions, y equals x and y equals x squared. So our first thing is that we're going to rotate around the x-axis. So visually, the blue curve is y equals x, and the green curve is y equals x squared. So since we're rotating around the x-axis, that means we're going to go in terms of x. And before we can set up our integral, we need to find the outer radius and the inner radius. So our outer radius is going from the curve furthest to the axis of revolution to the axis of revolution. So that means my big R of x is going to be x minus 0, which is just x. And my inner radius is going to be closest curve minus the axis of revolution. So little r is going to be x squared minus 0, which is just x squared. So now I can set up my integral. So I have pi times the integral from 0 to 1, because that's my intersection points. And I have the outer radius squared minus the inner radius squared. All right, so now I can go ahead and simplify before I integrate. So I now have x squared minus x fourth. I'm going to integrate that, evaluate at 1, and then evaluate at 0. The zeros cancel. And do a little bit more simplifying, and I get 2 pi over 15. All right, now we're going to use the exact same functions, but this time I'm rotating around the y-axis. So that means I'm going to need to change my functions in terms of y. So I'm going to find the inner and the outer radius first. So my outer radius this time is going to be the x squared function minus the axis of revolution. And this time, when I rewrite y equals x squared in terms of y, I get x equals square root of y. So I have square root of y minus 0, which just gives me square root of y. My inner function is just going to be y minus 0, which is just y. So when I set up my integral, I have pi times the integral from 0 to 1 of the outer radius squared minus the inner radius squared. I'm going to go ahead and simplify. So I now have y minus y squared. Integrate, evaluate from 0 to 1, simplify, and I get pi over 6. Now when you're rotating around a different horizontal and vertical line that are not the x and y axes, you have to pay very close attention to your inner and outer radius. So we're still using the same two functions, y equals x and y equals x squared. So for this example, we're going to rotate around y equals 2. So visually, this is what I have. I have my two functions, but this time my axis of revolution is the horizontal line of y equals 2. So that means to find my inner and outer radius, my outer radius is the curve that is the furthest away from the axis of revolution. So in this case, if I'm rotating at y equals 2, the curve that is furthest away is the green curve, which is y equals x squared. So that means when I do my outer radius, I'm still applying the top minus bottom rule. So this time my top is 2, my bottom is x squared. So that means my outer radius is 2 minus x squared. Now when I go ahead and do the inner radius, the curve that's closest to y equals 2 is y equals x. So my inner radius is going to be top curve minus bottom curve. So in this case, 2 minus x. Now I can go ahead and set up the integral. And so I have the pi times the integral from 0 to 1. And this is my outer curve squared minus my inner curve squared. I go ahead and expand, simplify, integrate, and evaluate to get 8 pi over 15. All right, now I'm going to take the same two functions, but this time I'm going to rotate around x equals negative 2. So this time I'm going to have my functions in terms of y, since I'm rotating around a vertical axis. So I still need to find which curve is furthest away from my axis of revolution. So that would be the green curve. And I'm still going to apply the rule right minus left. So this time my outer radius is going to be the square root of y minus negative 2, which gives me the plus 2. My inner function is going to be the blue curve minus negative 2. So I get y plus 2 for the inner radius. So now when I set up my integral, I have pi times the integral from 0 to 1. times the outer radius squared minus the inner radius squared. So then I can go ahead and expand, simplify, integrate, evaluate, and simplify again to get 5 pi over 6. All right, so now let's try some examples that with different functions. All right, so for this first example, you're going to find the volume of a solid that is rotated about the y-axis and is bounded by the following functions. So if I was to graph this, here is my x to the 2/3 function right here. X equals 1 right here, and y equals 0. So that just is your x-axis. So since I'm rotating about the y-axis, that automatically tells me that I have to be in terms of y, and I'm going to have horizontal rectangles. Go ahead and find the outer radius. So that means I need to use the function or the curve that is furthest away from the axis of revolution, so the y-axis. In this case, the curve that is furthest away from the y-axis is x minus 1. So that means I'm going to take right minus left, so I get that my outer radius is 1. Now for my inner radius, I'm going to take the x to the 2/3, rewrite it in terms of y. So right minus left, so I get y to the 3/2 minus 0, which just gives me y to the 3/2. Now I can go ahead and set up my integral, and I'm going from 0 to 1. So I have my outer radius squared minus my inner radius squared. Of course, don't forget the times pi. Now, for these examples, I did not expand all of the work. I just have the answer. You should be able to expand and integrate by hand on your own at this time. So after you do all of the work, your answer should be 3 pi over 4. All right, second example. Find the volume of the solid of revolution generated by revolving the region bounded by y equals 2x squared, y equals 0, and x equals 2 about the line y equals -8. So visually, this is what this looks like. So here is our y equals 2x squared, y equals 0 is your x-axis, and the line x equals 2. And we are rotating about the line y equals -8. All right, so I'm going to rotate this region right here, and I know I'm going to do it in terms of x because I have a horizontal line as my axis of revolution. So I need to do the outer curve or the outer radius first. My outer radius is going to be the curve that's furthest away, which in this case is 2x squared. And I'm going to follow the rule of top minus bottom. So in this case, my top curve is 2x squared, my bottom is -8. So I'm going to do 2x squared minus -8, which gives me 2x squared plus 8 for my outer radius. Now I'm going to do the same thing for my inner radius. Well, the curve that is closest to the axis of revolution is y equals 0, aka the x-axis. So I'm going to do top minus bottom. So 0 minus -8 gives me an inner radius of 8. So now when I set up my integral, I have my outer radius squared minus my inner radius squared. And then after doing all the work, my answer is 1,664 pi over 15. All right, let's try this one. Find the volume of the solid that is rotated about the line x equals 3 and is bounded by y equals x and y equals square root x. So visually, here is our graph and its axes of revolution. So the square root of x is your green curve, and your y equals x is the blue curve. Now, since I have a vertical line as my axis of revolution, I know I'm going to have to integrate this in terms of y. To start out, I need to find my outer radius, so that means I need the curve furthest away from my axis of revolution, which is the green curve. And I'm going to follow the rule this time, right minus left. So my right curve is the 3 minus my green curve in terms of y, which is y squared. Then my inner radius is the closest curve, so right minus left, so I get 3 minus y. So now when I set up my integral, I'm going to have my outer radius squared minus my inner radius squared and do all the work, and you should get 13 pi over 15. Well, I hope you enjoyed learning about the washer method, and I will see you in class tomorrow. Have a good night.